So differentials, 3.8 is all about differentials, and differentials very, very similar to derivatives. As a matter of fact, for the most part, you want to think about more like doing implicit differentiation. So if we wanted to find the differential of y, so we're going to write that as dy. It's very similar. We're not doing like dy dx. We're just really doing the differential of both sides of the equation. So it's more along the idea of like multiplying both sides by 2 or taking the square root of both sides of an equation. You take the differential of both sides. I'm not taking the derivative in terms of x. I'm just taking the differential. So it's going to be more like this. F prime of x dx. Okay. When you end up doing u substitution, you're basically going to be doing differentials for doing antiderivative. For the most part, you're going to use derivatives, but the differential is so similar. It's kind of sillily easy. All you gotta realize is you put a dx on the end of it. So in this case, like the differential for the volume of a sphere, so dv would equal 4 pi r squared, but then dr. Now the biggest place where this is useful is in finding error, and we'll see that in a second. All right, so when you want to find error, you're really looking for your change in whatever you're looking at. So like circumference, you're looking for your change in circumference or your change in volume, and that would be your propagated error. All right, so let's take a look at the problem. Josh used some questionable methods for finding the size of a soup can. The shoelaces were rather grungy, and we can only be certain about plus or minus 0.03 centimeters of the radius. Okay, so what this is dr. Also look a little shaky using the ruler, so his height might have ranged about plus minus 0.01 centimeters of height. So this is dh. Okay. If you measure this can's radius to be 4, so r equals 4, and h is 12, what's propagated error in circumference and volume? Okay, well, the circumference, and we're just looking at a can, is just 2 pi r. So propagated error circumference, your change in circumference is 2 pi dr. Okay, so our propagated error in circumference is, well, we just plug in the r.03 here, my dr, and I get about, well, change. I mean, you can put plus or minus on there if you'd like to. So it's just the error, which usually you don't do. You can do a plus or minus error, or you just say you have an error of this, meaning the plus or minus. So 0.06 pi. You can come to a decimal if you'd like to. That means that the error could be, it's within plus or minus 0.06 pi of the actual number. So if you plugged in your circumference, your radius would be 4, so we get 8 pi, basically plus or minus 0.06 pi. Those are kind of our error bars on there. That would be where I would expect the circumference to fall. As far as the volume, 4 pi, oh, sorry, I'm thinking sphere for a second. It's a can, so we have our circumference times our height. Okay, I want to do dv. Well, we kind of have to use product rule on this. So if I wanted to take 2 pi r is one and h is the other one, so the derivative of the first part, so 2 pi dr times h plus, and then leave the first part alone, 2 pi r dh. You notice the 2 pi just kind of could have gone with either of them. It doesn't really matter. Or you could have factored it out entirely and done the 2. But that's the basic idea. So our propagated error in volume is 2 pi dr times h. So dr we found to be 0.03 times h, which is going to be 12, plus. Now you might wonder about, well, what about the plus and minus on these? Do I have to take into account and like do 4 different options where this is plus, this is plus, this is plus, this is minus, this is minus, this is plus, and this is minus, and this is minus? Well, the truth is you want the outer limits, and that's where they're both going to be plus and they're both going to be minus, so they add together or they subtract together. So I mean, if I put a plus or minus out front of the whole final answer, I would get basically the exact same thing. I would get the error bounds I'm looking for. Okay, the R is 4, and the DH is plus or minus 0.01. And then from here, we just have to kind of work through this. So we can do it if we want to. So it's be 0.06 times 1272. So I think that's 0.72 pi plus 8 times 0.01, 0.08 pi. So I believe, unless I just multiply wrong in my head, that should be about 0.8 pi. That would be our error bound for our volume. Okay. So what did we end up doing? We took the derivative, basically, it's a differential, and the reason you know to do a differential is generally when you want to find any sort of error in something that you have like a formula for. Whenever you see that error, you're probably going to be doing differentials. If you got some sort of like change in R, plus or minus change in R, you're going to have to put that dr on the problem. If the radius was 4 period, there wouldn't be any dr and there wouldn't be any error. It would just be 8 pi period. The second you start talking about error, that's when you start doing differentials. And the only difference is you tack a dr on the end of it, just like you do with implicit differentiation. All right, we got one more here we'll do, and then we'll talk about relative error, and then we'll talk about percentage error, which is basically the exact same thing. All right, so you're going to have dice. Each die should have a side length of 1/2 inch, and Brianna's going to make us dice, and she's good, but her dice are only accurate to plus or minus 0.01 of an inch. Find the propagated error in the volume of the cube. Okay, well, first off, we'll start with the formula. Volume is going to be r side cubed. You could use x, you could use s. It does not matter. And so, since we're talking about some sort of error, well, we want to find dv. Our propagated error would be 3x dx. Oh, 3x squared, sorry. Now, be careful about using x, because people get so used to just say, okay, 3x squared, and don't put the dx. Anytime you start getting error, you got to use your differentials. So 3, and then we're just going to toss in 1/2 squared times r dx, which is 0.001. You see that plus or minus? That's going to be your dx, dr, ds, whatever it is. And then you end up getting this. So that's 3/4 times 0.001, or so what we got to do is we take our 3/4, which is 0.75, and if it was 1, which it's not, it's right here, 1, 2, 3. If it was 1, we would have this, but we have to move it left 1, 2, 3. So we end up with 0.00075. And now the question is, what is this unit, you might ask? Well, it's a change in volume, so you better make sure that it is in volume. Okay, so now the question is, how important is it? So let's say we have a propagated error of 2 miles. Okay, well, if you're talking about size of dice, that's not a big deal. But if you have sorry, that's a huge deal. If you're talking about size of dice, that's crazy. What if we had a propagated error of 1 inch for a die? That's still way too huge. But if you're talking about the distance between here and the moon, and you're off by 1 inch, that's probably pretty good. Or talking about the distance from here to Saturn, that's even better. So when we go through this, it depends on what you're talking about. Now, this is pretty good in terms of dice. I mean, I think so. I'm not really a casino runner, but see, it's decent. But it's really relative to the size of the actual volume. So what engineers are generally more interested in is the relative error that you have. So all you got to do is take your propagated error and you divide it by the actual volume. So let's say you get a propagated error of 0.003, and your volume of your dice, which was the 1/2, well, here, let me just use the actual numbers we had, 0.075, and then all you got to do to find the relative error is just divide it by the actual volume, your side cubed. Now this is I mean, when I say the actual volume, that's your assumed volume, not doing any plus or minus or anything like that, saying that the side length is a half. So you take 1/2 cubed, and this gives you whatever your relative error is. Now here's the good news. You want to turn it to percent error, multiply by 100. So this is only giving you your relative error, and multiply by 100, you get your percent error. Just move it over 2 spaces. There it is. All right, have fun.